So for the first part of 4.5, we're going to look at the tangent graph and some inverse graphs. So let me start out real quick. Let's identify the key points for the tangent parent function. So if we look at our unit circle, you'll notice on this one, it's a little different approach when you get to tangents. That's why these are separated from the sine and cosine graphs, because they come with some very different characteristics than sine and cosine do. For one, it's not a continuous graph, as the sine and cosine graphs are. This one comes with vertical asymptotes in between the periods. It also doesn't start at 0, right? We look at the parent function of a tangent graph is actually centered at 0. And so we actually look at how far to the left we should move and how far to the right we should move from 0. So we're going to start looking at the unit circle, but notice the order that this is going to go. We're going to start at negative pi halves and work our way to positive pi halves. So here's how this goes. So negative pi over 2, if I start here, right, if this is positive pi over 2, then going this way would be negative pi over 2. So we're actually going to start here, and we're going to work our way to this guy. So if I started at negative pi over 2, remember tangent is sine over cosine. So at negative pi halves, I am at negative 1 over 0, which, what do we know about negative 1 over 0? Anything over 0, right, is undefined. So at negative pi over 2, it is actually undefined, and so that's where we are going to get our first asymptote for the tangent graph. Let's move to negative pi over 4. So if I travel, so here's positive pi fourths. So we're going to travel to negative pi fourths. And again, if I did my sine over my cosine, y over x, you can see in this case, this divided by this would be negative 1. So that gives us the next point. At 0, sine over cosine would be 0, positive 1, undefined, right, to finish off the chart. So 0, 1, and then another undefined, and so you can see that at positive pi over 2, we have our next asymptote. So one of the other main differences we see with the tangent function is instead of the period being 2 pi, like the sine and cosine graphs were, a period on the tangent function is simply 1 pi. As we traveled from negative pi halves to positive pi halves, we only went halfway around the circle, right? So it's only pi units for the tangent graph. So if I were to plot these 3 points, so at negative pi over 4, I am at negative 1, and then 0, and then positive 1. And if you were to plot more points, the shape that you're going to see on this is our S-shaped type of a curve. Right? Because remember, as we have vertical asymptotes, your graph will always approach the vertical asymptote by either headed towards positive infinity or it will head towards negative infinity. Right? So that's the parent function of our tangent graph. So 2 quick side notes over here. That's going to be different than sine and cosine. In this case, in order to get the period, instead of it being 2 pi over b, it's now just pi over b. And in order to figure out where those vertical asymptotes should go for a function, if we do the period divided by 2, that tells you how far to go left and right from the center of the graph. So on this one, remember the period was pi. If I did pi divided by 2, like this is telling me to do, that would be pi over 2. And so what I wrote here was, if this is my center, if I'm centered at 0 like the parent function is, then I would go pi over 2 to the left, and I would go pi over 2 to the right in order to get my vertical asymptotes. And that shows me where one period is, right? So even though it's not a continuous function like sine and cosine was, it is still continuous within those vertical asymptotes. So within one period, it is continuous, right? But then you would have another one here and another one here, right? And it goes on and on forever. This is just one period of the graph. You can check out the key property summary box on page 464. I'll leave that one up to you. It'll help define some of the things like domain and range. Obviously on this one, we can see as far as domain goes, it's limited, right? Our domain would depend on how many periods we graph. But again, it's in one period of the parent function, its domain is only from negative pi over 2 to positive pi over 2, non-inclusive. The range, however, is from negative to positive infinity. So let's look at one of these with some stuff thrown in, like some transformation stuff here. So if we were going to graph negative 2, tangent of x minus pi over 4, so one thing we'll notice right off the bat is this has a horizontal shift, or called a phase shift when we're doing trig functions. We also have a vertical stretch factor of 2. We also have a reflection. So I try to throw a bunch of things in here so you can kind of see it all. So I want to start on this by just recognizing the period. So in this case, you can see our b value is 1. So our period is still pi units. Right? If I did pi over b, pi over 1 is still pi. So if I divide this by 2, this tells me that I'm going to move left pi over 2 units to get a vertical asymptote, and I'm also going to move right pi over 2 units to get a vertical asymptote. But I'm moving from the center, so I need to know where this graph is centered. The parent function was at 0, but this one has been moved to the right pi over 4 units, right? So this guy from here was actually moved to pi over 4. So that's where this graph is now centered. So from here, if I move pi over 2 to the left and pi over 2 to the right, I would get my vertical asymptotes. So if I subtract pi over 2 from this guy, so what's pi fourths minus pi over 2? It would be negative pi over 4. So there's our vertical asymptote on the left. And if I add pi over 2 to this guy, so if I did pi fourths plus 2 pi over 4, I get 3 pi over 4. So there's going to be my vertical asymptote on the right. You'll notice on this one, there are still 5 key points for a tangent function. However, 2 of those are for the asymptotes. So we're really only going to plot 3 points on this graph, right? Because the bookends are vertical asymptotes. So I left room for a point here, here, and here. Okay, so if this is centered, so again, I want to find the middle of these two guys to see where this point should be. So that would be at 0. And I want to find the middle of these two guys to see where that point would go, right? So obviously we're counting by 1/4 here, right? So this is negative 1/4, 0, positive 1/4, 2/4, which is a half, so you could write it as pi over 2, and then 3/4. So we should be counting with regular intervals, right? So they should be the same length as you count through this. So anyways, I look at these points. Again, there was no vertical shift on this, so I know my center point is still at y is 0. So there's our center point. Our vertical stretch on this, right? So it's like we're multiplying this times the parent function values, right? So in the parent function, I went from negative 1 to positive 1. Well, if I multiply those by negative 2, I'm now at positive 2 and negative 2. So remember, 2 things happened on this. One thing was the vertical stretch, so it went from 1 to 2. But then I also had the negative, which caused the point that was down here to go up there, and then vice versa on this side. So now I can draw my new sketch, try to squeeze it in here. It looks something like this. So there's our tangent function. I threw in just a side note on this, because when you graph a cotangent graph, cotangents are going to work a little differently, simply because a cotangent is obviously the inverse of a tangent. Something on the unit circle real quick. So just as tangent was y over x, right? When we do a tangent value, like we started here, we did negative 1 over 0. Well, what would cotangent do? Cotangent would do 0 over negative 1, right? It would flip. No idea what that is. So anyway, so instead of going y over x, for cotangent, you go x over y. because it's the inverse. Well, now it's no longer undefined, is it? If I did 0 over -1, I get 0. So I actually get a point now on the graph instead of an asymptote. So the location of the asymptotes change when you are doing a cotangent graph versus a tangent graph. The points that were 0 on tangent are your undefined points for cotangent, and vice versa. So if I now did on this one, again, remember this was y over x when I did tangent, and it came out to be 0. But now that it's cotangent, I would do x over y, and now it's undefined. So what does that mean? So as I look at the, let me refocus. So as I look at the cotangent graph, this is the parent function for my cotangent graph, right? So instead of being centered at 0, right, and my vertical asymptotes were here, now all of that has flipped. So now instead of being centered at 0, my asymptote is at 0. My period is still pi, right? But now it's from 0 to pi rather than negative pi halves to positive pi halves. So it's basically like it did a shift of the tangent graph over pi halves units. But you'll also notice that it now goes this direction in the parent function rather than the positive direction in the parent function. So really what you see in the cotangent parent function is this. It's the tangent graph that's been moved right, pi over 2, and it's also been flipped. Right? So that's what's going on in order to create the parent function for the cotangent graph. So it looks like that. Let's graph one. So I changed the period on this one as well as threw in a vertical shrink on this guy. So for my cotangent graph, again, my period is pi over b, which in this case, my b value is pi. So pi over pi. So my period is 1 unit. Right? It's no longer in terms of pi for this one. Now it's just, I'm going to get nice integers on this one, which is probably easier anyway. So if my period is 1 unit, so remember the parent function here went from 0 to pi. That was the period. So it's going to go from 0 to something as long as there's no horizontal shift. This one does not have a horizontal shift, so it's going to go from 0 to 1 for this guy. So let me throw in the asymptotes on this one. There was no horizontal shift, so we're just going from 0 to 1. And in the parent function, remember that the points were here, here, and here. So at, let's see, if that is 1, that means this is 0.5, which means this is 1/4. This is 1/2. This is 3/4. Those are my points. So in the parent function, it was 1, 0, and -1. We got a vertical shrink by 1/2. So if I multiply these values by 1/2, I am now at here, here, and here. Right? So those would be the 3 points that we would actually see on this graph. So anyway, if I connect the dots, we have our cotangent graph. It would look like this. So how do you check this on a calculator? How do you do an inverse function on a graphing calculator when there is no button that says cotangent, right? Or cosecant or something like that. So simply just keep in mind what an inverse function is. It's 1 over the original function. So if I want to graph this guy, it would look something like this, right? I got my 1/2. So since it's the cotangent of pi over x, I'm simply going to type in 1 over the tangent of pi x. So that would be the inverse, which is cotangent. And so that's how I would type it into the calculator. My window, I just went from 0 to 1 in my window. And the range is infinite, so any decent range would be fine for this. So if I graph it, again, I'm going to get the similar shape. It's a little more spread out because of the window I use, but anyway, we can see it's still the same shape that I graphed when I did this by hand. Let me keep it moving. 2 more, 3 more, 3 more. I'm trying to give you guys, 2 more, sorry. I'm trying to give you guys a sample here to get you through any problem that you will face. So for the cosecant graph, when you do an inverse function, and you may or may not have been exposed to this in Algebra 2, I'm not sure. That may vary from year to year depending on how much time they have. But an inverse function, when you get to sine and cosine, simply take on the reciprocal properties of the parent function. Here's what I mean by that. This is the sine graph, right? That's the parent function for sine graph. So what would be the inverse of sine, right? Or in other words, cosecant. What would that look like? So what we see in cosecant, similar to what we saw with the tangent and cotangent, remember the things that were 0, so where you see the zeros, right there, and right there, well, what happens when you take a 0 value and do the reciprocal? Well, you're putting 0 on bottom, and now it becomes undefined at that point. So the inverse of sine, where it used to have zeros, would now become undefined values. And that's where we get our vertical asymptote. So wherever you have a 0, as you do the inverse function, your zeros become vertical asymptotes for an inverse. So I get those guys right there. And again, if I look within each little interval, so I have a little interval here, I have a little interval here, all of these points also get flipped. So instead of it now heading downward from its peak, it would now head upward. And I can do that for as many intervals as I see. This is only one period, so we could certainly carry this on into more periods. But anyway, that's what the cosecant graph looks like. So essentially, when you graph these, we graph the original graph. But keep in mind, as far as our answer is concerned, the original graph is excluded. My answer is this U, and that's it, right? This graph is not part of my answer. It's simply what we use to get the answer, right? So let's try that with a cosecant graph. So for this one, again, I want to start with just the sine graph. So go back to your basics of graphing a sine graph. I would start with my period, which is 2 pi over b. And in this case, my b value again is 1, so it's 2 pi over 1, which is always nice. Easy number to work with. I'm going to divide that by 4 to tell me how often I should be making my marks. So if I divide this by 4, that tells me every pi over 2 units I should be making a mark. In the parent function, it would start at 0 and end at 2 pi. But this guy has been shifted to the right pi units, right? So instead of starting at 0, it would now start at pi. So a couple things to consider here. If I'm starting at pi and the period is 2 pi, where will I end? Well, I'm going to end at 3 pi, right? Because from 1 pi to 3 pi is 2 pi units total for one full period. So I'm going to end at 3 pi. And this is going to get tight real quick, I can tell. So let me write small. So what about the values in between? Remember, I'm making a mark every pi over 2 units. So if I started here and add pi over 2, see if I can break this up evenly. So if I add pi over 2 to this, I'm now at 3 pi over 2. Add another half, and I'm now at 2 pi. Add another half, and I'm now at 5 pi over 2. Add another one, you'd be at 6 pi over 2, which is 3 pi. So there's my 5 key x values. So for this one, let's take a look at, we know the basic sine graph would start at 0. It goes amplitude, 0, lower amplitude, back to 0, right? That's what the sine graph would do. In this case, we do have a shrink, vertical shrink. So instead of going all the way up to 1, I'm actually now only going to a third. So this will be a very small graph. In fact, I'm going to do this in red to make it stand out. So it would start at 0. It goes upper amplitude, back to 0, lower amplitude, which is negative 1/3, and back to 0. So here is the sine graph. Would look like this. So remember, what we're doing is we're not graphing sine, we're graphing cosecant. So I'm using the red graph in order to get my answer. So I'm going to do my answer in a different color here. So remember what we see on this? I have a vertical asymptote now at the zeros. So I'd have one there, I'd have one there, and I'd have one here. And I just do the reflection of the red graph within those intervals. So I would have part of it would go here, part of it would go here, right? And that's just one period. So again, if you take the red graph out, you actually have your answer. And we'll do this on the calculator in a second. What if I wanted to extend it for more than one period? What if the directions say graph for 2 periods or 3 periods? How do we keep it going? Well, real simple. I just keep going with the process. I'm counting by pi over 2. That's one of the reasons I like this method, because I can then, it's easy for me to extend it in either direction because I can keep adding pi over 2 as much as I want. I could subtract pi over 2 as much as I want, and I can keep extending it that way. So if I did extend this one further, see if I can get this as straight as I can. If I keep adding pi over 2, let's see, this was 3 over 1, so 6 over 2. Add another pi over 2, and I get 7 pi over 2. And then 8 pi over 2. And then 9 pi over 2. And then 10 pi over 2. And there we have another period, right? So I would start here. I have an additional 4 points, so 5 total, right, to get this extra period. And you'll notice, remember what we said, 1 full period is 2 pi. So this next one's going to go from 3 pi to 5 pi for a full 2 pi units. And so I'll just carry on the pattern. I go up 1/3, back to 0, down 1/3, back to 0. So there's that. I can throw in more asymptotes. And I can throw in more of my cosecant function. So now I've actually graphed it for 2 periods rather than 1. Right? And of course we could keep going on that all day. So, but that's the gist of what it looks like. How would we graph it? So it's a little tricky when you go to punch this in. You have to really sort of overdo the parentheses to make sure everything gets written in correctly. I got my 1/3, piece of cake. But obviously instead of cosecant, we're going to do 1 over sine. So I overdo parentheses here to make sure everything gets placed properly. So I'm going to say 1 over, and now I'm going to open up another parentheses to make sure my calculator recognizes that everything I do next is on bottom. So I'm going to say parenthesis sine of x minus pi, close, close, close. So it looks like this. I changed my window to go from 1 pi to 5 pi, so I just typed that in for my x minimum and my x maximum. I just hit pi, and then I just hit 5 pi. They show it as a decimal, but I typed it in as pi. And then your range is whatever, because this goes up and down. So anyway, let's hit graph. It should look exactly like what we did on our paper, the blue marks anyway, right? So you can see it's going to go on for the same 4 chunks that we did, and that's what we got. So you can do these on the calculator. Last one. I threw in a side note on this one. I showed earlier in the previous lesson, I believe it was, how the cosine graph is simply a horizontal shift of the sine graph. Right? I went over that in a previous video. Likewise, cosecant and secant do the same thing. Right? So this is the inverse of sine, this is the inverse of cosine. So really this is simply also going to be a horizontal shift of the cosecant graph by pi has units. So it goes something like this. I'm not even going to try on that. We'll just graph one here. We'll finish up this way. So let's graph a secant graph. So I got pi x over 2. So my b value is pi over 2, right, on this one. So anything attached to x is your b value. So again, I'm going to start the same way. I'm going to say 2 pi over b in order to get my period. My pi's cancel. 2 times 2 is 4, so this is going to be 4 units. That's a nice easy number to work with. When I divide that by 4, so if I did my period divided by 4, obviously I just get 1, which means I need to make a mark every unit, every 1 unit. So this one, there's no horizontal shift, which is nice. So instead of going from, say, 0 to 2 pi like the typical function would do, this one's going to go from 0 to 4, because that's what we determined right here. So this one should go from 0 to 4. And I should be making a mark every 1 unit. So it would go from, I start at 0, right? So then I'm at 1, 2, 3, and naturally I land on 4 at the end of it. So there's my 5 key points from 0 to 4. Those are my x's. So if we apply our information that I'm seeing here, remember that the parent function of a cosine graph doesn't start at the center, doesn't start at the midline, it starts at the amplitude. And so in the parent function, it went from 1, 0, negative 1, 0, 1, right? That was the parent function. These guys are being multiplied by negative 2, right? So they're not only doubling, so we get the vertical stretch. So instead of starting at 1, it would start at 2, but I'm also getting the reflection, so I should be starting at negative 2. So my cosine graph starts at negative 2, then goes to 0, then goes to positive 2, back to 0, and negative 2. So the cosine graph, and I guess I'm using different colors on this one, that's okay. So my cosine graph would look like this. Of course, if we're going to do the secant function, just the inverse of cosine, again, my asymptotes will hit the zeros. And I think I'll show you something on this one. If I just graphed it for 1 period, so if I just did the reflection of, see if I can do this right, of the blue graph, then it should look something like this. Now, that can be a little tricky. A lot of times we might think of going this way with it. It can be a little tricky if you only do 1 period as far as these lower guys, but let me show you why that is what it is. If we were to carry this on, and this will be a real rough sketch because I'm just trying to make a point here, but if I carried it on, remember what your cosine graph would do. It would do this. Right? If I carried on the cosine graph, this is what we would see. Right? So remember the secant graph is the inverse of those. So I am flipping, and here you can see more of it now if I continue this. So we're flipping the cosine curve to become the secant curve. And so it's going to really look like that, right? Similar to what I did on the one up above. So only the red graph is our answer, right? So really the blue graph is not actually there. We used it as a guide to get the red graph, which is our secant graph. And again, you could always check this on the calculator the same way I showed you with the last one. But that is it for part 1 of this lesson.